Alrighty. Thank you for attending this talk. I have the honor of talking about a vision for transforming 21st century pedagogy via open standards, in particular OpenPOWER. This is part of the curriculum track, and before I actually even talk about the vision, I wanted to give you a little bit of perspective of where I'm coming from. Just briefly, and I'll jump back to this title frame in a minute, but just briefly, if you look toward the bottom of my professional background, you'll see that I have a number of academic appointments, working in government national labs and in industry. And so I think I have a unique perspective in terms of the need to teach architecture and system software, runtime systems to the students, and to provide a curriculum that bridges from academia to industry. And the government labs in between, if you will, where in fact the power architecture powers the two fastest supercomputers in the United States, and previously one that was fastest in the world, which was the Summit supercomputer. So that gives you a little bit of background about me from academic government national lab and an industry setting. And what we're here to talk about today is what I have as a vision for teaching these interrelated areas of architecture, computer organization, computer systems. And I think that we're at a crossroads right now that could lead to another, I would say, pedagogical evolution. Or revolution. The first one occurred in the early 90s, which was spurred on by research in the 1980s that reevaluated or revisited RISC as architecture for the industry as well as for teaching purposes. And so with that in mind, let me talk about the teaching perspective from the 1970s, which is 50 years ago, before many of us were born, to today. This is what you see on the left here is a traditional software stack, from the hardware to the computer architecture and organization, then up to the system software and runtime system, and then middleware and the application over top of it. And with the hardware, we tend to look at designing and simulating digital circuits, like you would traditionally do in an electrical and computer engineering program. Computer architecture and organization, you could look at pedagogical architectures and then try to bridge it over to the real world. And then with the system software and runtime system, with the advent of Unix and C in the 70s and 80s, that's really where the curriculum gets taught from for system software and runtime systems. So what I'm going to talk about today is more the pedagogy of the lower three layers, and in particular, looks like it's just barely fitting. If you look at the curriculums on the two rightmost columns, CS, which stands for computer science, and ECE, which stands for electrical and computer engineering, you see that on the CS side, at the lowest level, the students typically use tools like Logisim or SPICE with a user-friendly interface, and hiding a lot of the lower level details. On the ECE side, you'll see more increasing use of FPGAs in the area of Verilog and VHDL, or register transfer languages in general. And then from a computer architecture and organization standpoint, back in the 70s, we were 70s and 80s, we were looking at CISC-based architectures like PDP-11, the VAX-11, which was the successor to the PDP-11, IBM System 360 and System 370, and as well as the x86 architecture. And then that transformed in the mid to late 80s, and then finally into the in the pedagogy arena in the 90s. It transitioned to RISC-based architectures like MIPS and LC3. LC3 only had 15 instructions, and many more. And then finally, in the system software runtime system, what we saw is this use of Unix and C and x86 and Linux became in the 90s came to the forefront. And so I should put a little arrow and note the addition of Linux into the mix of this. So this is the high level perspective from the 70s and until today. And so if we look a little bit more at the details of this, the history is that in the 70s and 80s, we had the CISC architecture. From DEC, we had the PDP-11, VAX-11, which I programmed on many hours inside a cold machine rooms at the time. And then there was also the IBM System 360, IBM System 370. From Intel, we have, of course, had the x86 architectures, and Motorola had the 68,000 series architectures. And these were all CISC-based architectures. I'm sure I may be forgetting or inadvertently leaving some CISC architectures off, but these are the more prominent ones that were in the forefront of teaching at the universities and colleges out there. And these are the types of textbooks that were used to teach computer organization and architecture. So the Hammaker, Verancic, and Zaki's book was highly prevalently used to teach CISC-based architecture. It evolved a bit to start to reach out to RISC architectures. But it was primarily a CISC-based textbook, as are the other two that I'm showing. And these were textbooks that were prominently used at universities and colleges through the 80s. Okay. So in the 70s, 80s, we had this complex instruction set computing, and this pedagogical revolution that occurred, it occurred, say, around 1990, maybe late 1980s and early 1990s. And it was spurred by research in the earlier 1980s that revisited RISC architectures that was pioneered by John Cook at IBM. And it resulted that research in the 1980s that revisited RISC architectures resulted in a seminal textbook that is known as Computer Architecture, a Quantitative Approach, and its subsequent prequel book entitled Computer Organization and Design. And so we had this RISC, and the DEC went to the alpha. MIPS started out with this deluxe instruction set, and then moved to the MIPS, and Sun had Berkeley RISC, and then that became Spark. And so these are the series of textbooks that evolved from this pedagogical revolution. And so what ended up happening was, let me see if I can bring up the laser pointer. No, it's not letting me. Oops. Okay, so I'll have to go without the. Hopefully, you guys can see a pointer. So this book in the middle bottom, Computer Architecture Quantitative Approach, came out first, and many institutions adopted this as part of their curriculum in the as a senior level, graduate level course. 4 or 5 years later, this prequel book came up and got deployed in the sophomore and junior levels. And I'm going to talk a little bit more about this in a tabular format so that you can see the organization of this. And then later on, Color and Singh from Berkeley came up with this textbook called Parallel Computer Architecture that is eventually taught in a lot of graduate courses in architecture. Okay. That has further evolved from the 2000s to now. We've had this RISC proliferation. Now we have MIPS, Sun, ARM, IBM, Power, RISC-V. And that proliferation then was followed by systems programming, but with a CISC environment, a CISC x86 environment, which is a proprietary ISA, of course. And so this led to an issue of a disconnect between the architecture, the way we were teaching architecture with RISC orientation versus the system-based programming that is taking the CISC orientation. And that CISC orientation for systems programming is captured by a book that is quite prominently adopted called Computer Systems, A Programmer's Perspective by Bryant and O'Halloran from CMU. And the purpose of this book here in this bottom right was that past systems books tended to focus on one aspect of the system or the other. So you focus on hardware architecture, or you do the focus on the OS, or you focus on the compiler, or you focus on the network, or what have you. And the idea was that this book would span all of these environments, but do so from the programmer's perspective. So if you will, more of a top-down approach. Which then effectively ignored the architect's perspective due to the proprietary nature of the x86 ISA and the underlying architecture. So while these books here, you can see up at the top, these are the 3 books here at the top are essentially the same book. It's just that they've catered it around specific instruction set architectures, MIPS, ARM, and RISC-V, and then Computer Systems, A Programmer's Perspective, is catered around the x86 architecture. Okay. And so one might argue that while each of these books served as exemplars for each of their respective ISAs, you could argue that the use of these disparate ISAs from MIPS to ARM to RISC to x86 serves as an unnecessary learning impediment or obstacle and source of confusion with undergraduates that are just first getting exposure to the underlying computer architecture and organization. Okay. So the idea here is, is this time for another pedagogical? I've put revolution, but it's probably more of an evolution than a revolution here. And so let's take a quick look at, I started out at really high level and I've been drilling down. So let's take a look at a typical curriculum. And so for architecture and systems, and I'm sorry, it looks like on my display here, it's got cut off on both the left and the right edges. But for this typical curriculum with architecture and systems, you'll have a, So I should note that this is a generic curriculum, a set of courses that is widely followed throughout higher education. So what you see here is this is Digital Design and Intro to Computer Organization in the top left, and an example textbook that would be used is Introduction to Computing Systems from Bits and Gates to C and Beyond. It used the LC3, which stands for Little Computer version 3. ISA, it had 15 opcodes. It's a very simple RISC-like language. It's an academic ISA. It's mainly for pedagogical purposes, and it's generally taken in the sophomore year. It then evolves to computer organization, which is then taught generally by a book called Computer Organization and Design. And that was the one that I showed on the previous slide, where they had the MIPS edition and now also the ARM and RISC-V edition. And so this is for the embedded space. Oh, I'm sorry. It was as an academic ISA, academic ISA, but it quickly became real world with the MIPS and Spark architectures, and now it's more real world in the embedded space. And this is typically taken in the sophomore or junior year. Following that, with the knowledge of the underlying hardware, a sufficient exposure to the underlying hardware, then students take a computer systems approach. A computer systems class, and that's the programmer's perspective book that I was telling you about, and that one's the x86 ISA, and it's a real world ISA. It's not one that one would typically use to teach ISA or assembly language, just because it's an overly complex CISC-based instruction set architecture. This is taken in the junior and senior year. And so already what you see, and if you go back off to the right, you've got this disconnect in terms of ISAs and going between LC3 to MIPS, and then MIPS to x86, and now x86 finally to the computer architecture book, which started the RISC revolution, and this is Computer Architecture Quantitative Approach. Okay, so these all underlie subsequent architecture and system courses, say in operating systems, parallel computation, network architecture and programming, and compiler design and implementation. The focus here is that, well, in terms of a vision for 21st century pedagogy in architecture and systems, we can't tackle this all at once. So what I'm showing here is decades worth of effort in terms of pushing out teaching academic environment material. And so the focus was going to be in the red box area that I have shown here. And this is a little bit tongue-in-cheek. What I'd like to see with this vision is we want to transform the wild, wild west into kind of law and order. So from this environment where we have these current set of textbooks and curriculums around these textbooks that are around MIPS and RISC-V and Intel, and being a source of confusion and sometimes not being able to, if you will, connect the dots across the different types of ISAs, particularly given that two are RISC-based and the third one is CISC-based. The idea is to transform this into an environment where you could have a sequence of 4 classes or a set of 4 classes that are integrated around a single ISA, such as OpenPOWER. I mean, this is, I mean, there's a bit of a cliche or saying that I don't remember exactly where it came from, but there's this notion of like, you can't really connect dots going forward, but you can, if you look backwards and you connect the dots in the past. So like if we're looking at architecture all around OpenPOWER, it'll be easier to connect all the dots together in terms of then moving forward with OpenPOWER as an example for further architectural systems research. All right. So this is one approach may be, well, let's just take these different types of textbooks from MIPS to ARM to RISC, and let's just create a new one with OpenPOWER. So rather than try and do that, which is what we've decided not to do. The reason for not doing this is that one is it'd be a massive undertaking. Two, it would be a challenge to get this type of textbook or curriculum adopted in the heart of an undergraduate curriculum, that is in the sophomore and junior year. And so the idea is, instead of starting here, is to start with the computer architecture quantitative approach textbook and associated class that is typically taught as a senior level or beginning graduate level course, and take leverage what's there with respect to MIPS, transform it more to looking at the OpenPOWER ISA. And we're going to start this by updating the lecture material to incorporate the Power ISA, and you'll see a brief update of that in the next slide. We also want to add an OpenPOWER case study at the end of each chapter. And the reason for this is that in this textbook right now, many of the chapters have case studies for particular ISAs that extend upon the MIPS-based text in the chapter. I'm trying to remember this off the top of my head here. I think, like, for chapter 2 in the memory hierarchy design, it's all about it's MIPS oriented, and then at the end of the chapter there is a section that looks at the memory hierarchy in the context of the ARM ecosystem. Let's see. And then in addition to adding a case study at the end of each chapter, we then would seek to supplement each chapter with additional OpenPOWER exercises, much as what is sporadically done in the chapters with ARM-based and x86 exercises. There are actually also some power exercises. Those are a little bit fewer. And then, in addition to supplementing it with these exercises, the idea is to plant the seeds for using OpenPOWER ISA as for capstone projects and research projects, particularly given the fact that OpenPOWER is not just an open source specification, but it is an open architecture, open source processor. Okay. Let's see. So at the present time, we're in the process of rolling this out for the spring 2022 semester. There is expected to be on the order of 100 seniors and graduate students taking this elective course. For the seniors, it's an elective course. And then deploying this to 4 U.S. colleges, well, Virginia Tech included, and then scaling beyond that, ideally, if possible. So right now, so far, the lecture material, we've already updated chapters 1, 2, and 3 in the Computer Architecture or Quantitative Approach textbook, and you can see what the names of those chapters are there. We've also looked at in terms of the exercises. We've looked at just the standard Linux command line and various benchmarks in order to identify architectural features that they can look at. So looking at /proc/CPU info, that kind of thing in terms of the command line, doing benchmarks like the stream benchmarks to really find out what the bandwidth is available to the memory system, and so on. And then we're also looking to leverage the various tools, open source tools that are out there, including Gem 5. There was mention of Power Gem 5 in the previous I think of the previous talk as well, which debuted in OpenPOWER Summit 2019, microwatt and the Power 10 functional simulator. So that does it. That gives you a high level overview of what the vision is and what the status is. Ideally, we'd like to have these core set of 4, anywhere from 3 to 5 courses around a consistent ecosystem, so that it makes it easier for the undergraduates to connect the dots between the different courses, and then being able to leverage that in moving forward with capstone projects and research. And just a brief acknowledgement is to IBM and Virginia Tech for supporting this, and for allowing us to giving us the means to pursue this, and for Virginia Tech to giving us the platform with which to deploy this to the university and then beyond to the other universities. So I'm going to backtrack to this particular slide and leave it here to ask for questions. I mean, this to give you an idea in terms of updating lecture material, we haven't updated everything, but a lot of it has been updated more with respect to power. Some of the things that we're still working on, and we welcome any help from the community. I have my contact information down at the bottom of the slide, along with a phone number. This is just one example of many examples that I have in the lecture material, which will be all pushed out as open source and freely usable by the spring. Needing to update these types of things. So these numbers and this data is all Intel data. It was pulled together by Intel and Kunle Ulukten from Stanford. We'd like to get this updated for IBM Power. So with that, that's all I have for today. I hopefully left enough time for some questions. I was told to do like 30 minutes and try to leave time for about 10, 15 minutes of questions.
Yep, I see. Right. We have about 15 minutes for questions.
Okay. Oh, so the display is not clipped for. Okay, good. So I see a question: how would students get to program on Power? Do you have hardware access? That is an excellent question, because these are things that we were looking at dealing with in terms of the Linux command line and tools and things like that. So because folks won't necessarily have the Power architecture, or even FPGA boards where you could run a Power simulator or emulator like microwatt, you can run on an FPGA. Because institutions won't have that, we're looking to also create exercises and case studies that leverage simulators like Gem5, which you can run on any platform, and it will simulate the Power ISA. So there's multiple solutions here, and so I showed earlier the CS and ECE columns, and on the CS side we would make more use of things like Gem5 or the Power 10 functional simulator, which you can run on any computer. On the ECE side, you could then use something called, there's a project called Microwatt that you could run on FPGAs, in which case then you would need to get the development boards. We actually also happen to have some IBM nodes that we can deploy and ask students to do hands-on exercises on those as well. I don't know if I answered that question. Are there development boards? and it looks like somebody's answered, Mendy's answered the OpenPOWER Hub, they'll have free access to power. So, relative to the exercises that we put out, we can put the exercises out to run on simulators, emulators, and then as well as real hardware as people have access to the resources. But we're tackling all of them just because if folks are hard pressed to be able to get access to the actual hardware, they can always run it on the simulator. In fact, I just take a moment to say that relative to the simulator for Gem 5, the support for power is pretty thin. A student that's working on it with me had noted that I think the power support left off like power 2 or power 3 and has not been updated. And so that's one of those things that we could look to have as say an exercise, a massive exercise, or a semester project in a computer architecture class like this. How much interest is there in FS? I'm assuming FS is file system support. This is from, it looks like it's from Boris Shingarov.
Yeah, let's just talk if I can unmute maybe this
yeah,
is
sure.
I'm the maintainer at Gem 5 looking at the Power ISA. So what we did the last year was we took Sandeepan's Power Gem 5 and started upstreaming all that work because it was, kind of rotting in some other repository and not being helpful. And we got it where all of these interesting things about, like, we now have 64-bit support, for example. So the whole everything that is in SE mode, right? The user land only, that's all upstreamed. And now we would like to continue with FS support, that is the full system support, right? So that you can model how the Linux kernel boots on it, and you can actually do all the system level stuff. But frankly, we just, well, first of all, we don't have enough bandwidth because with SE, like, I use Gem 5 for compiler research, and that is kind of directly relevant to what I am doing. But with FS, like, yeah, I mean, that I will spend little by little time looking at these commits, but it's going very, very slowly. And well, frankly, I'm not sure how wide of an audience there is for this. I mean, this is very encouraging to hear from you that somebody is using this or trying to use this. So it's not completely, uninteresting to anyone. But realistically, like, can we maybe, I don't know, maybe we can have really a co-op student working on full system,
Right.
Maybe,
Yes.
I just feel like I am in a vacuum and I don't know how many potential users are for this thing even.
Right. Right now, I would say that the number of users probably isn't as large as we would like, but I think that if there's enough critical mass around this, that there would be at least support, interest in supporting SE. I don't know that we need full system support. By that token, though, it's certainly one of those cases that for a graduate level course, if we could set this up as a project for students to then develop and then commit to a repository, there could be some some leverage there. Now, the problem is of course the longer term maintenance of that, and so I don't have a good answer for that. But I mean, it's one of those things that if there's sufficient critical mass and the ball can get rolling enough, maybe there'll be more volunteer or grassroots support and committing of resources to this. It looks like there's somebody. There's a couple of chats that came in. Yeah, so Atharva, who's a student who's working with me on this, has noted that we haven't come across a use case for full system simulation yet, and that SE is sufficient for now.
Yeah, well, SE is done at this point. Like starting with the June release, SE is completely there. And it's really, it is a chicken and egg problem, because when you don't have it working, people on the Gem 5 the main Gem 5 development team, they say, oh well, this is abandoned, nobody, like, it doesn't even work, you cannot really do anything serious with it. And because of that, they look at it like, it's abandoned legacy, we're not gonna work on it. And when you start actually actively contributing to it, like I did the last year or the last few years, they kind of change. Oh, well, it turns out that this is actually useful for somebody, and more people are coming. But it was just not enough to really kick off development of full system. But SE, we are pretty much in very good shape. Like, everything that was in Power Gem 5 is now upstream, and we added more.
That's good to hear. I mean, I think that I'd love to talk with you more offline with respect to what we could do, at least for this coming spring semester, for example, in terms of further extending support, or just showing showing the GEM community that this is going to be used, and you'll get upwards of hopefully 100 users this coming spring.
Okay, let's connect offline. I'll send you an email.
Excellent.
I have this. I see this at the bottom of the slide, so that's.
Yeah, I can just stick it in here.
Okay, thanks.
Thank you. Are there other questions? That was very, very useful. Thanks, Boris, for bringing that up. It's really good to see that it's as far as it is, and I mean, it'd be nice to have full system support, but it's not necessary, because I mean, full system is a very daunting task to do, and just maintaining even what's there already is a big task. So.
Hey, this is Todd. I was just wondering, you're making this curriculum available to everybody, right?
Right.
Yeah. Right. So how and how are you going to do that? What's the mechanism for rolling that out? Do you have that figured out yet?
So it's going to be so we don't have it completely figured out. What's in the back of our head right now is to just roll it out internally to the entire campus via a system. It's called Canvas, which is an academic teaching environment, and then it has, get out all the bugs and refine the curriculum and the exercises and the case studies further, and then deploy it at the end of the semester via either just a website, or through a GitHub. I mean, even though GitHub is usually used for typically used for code development and not whatnot, thinking of pushing this out to a GitHub repo where people can then download in different versions of the material as it evolves over time.
Yeah, okay, that makes sense. You can put it out on, the OpenPOWER Foundation has a Git repository as well. We could toss it on, but yeah, we can.
So yeah, I mean, that would be good. I mean, if you could, yeah, if you could help me connect the dots in terms of like, if it's something that we don't have to set up our own repo that's specific to VT, that we could instead connect to somewhere up to the OpenPOWER repo, that would be fine as well.
Yeah, okay, that sounds good.
Anything else? Okay. I guess do I just yeah, stop sharing and.
Yep, we're at time, so thank you all for attending. And just a reminder, the next session will be starting at 1 o'clock. And thank you, Dr. Feng.
Great, thank you. Thanks, everyone.